Yes, okay. So quickly about us at GerritForge, we're sponsoring these events. I guess you all know us by now, but anyway, we're a US corporation incorporated in Sunnyvale in 2019 and deeply committed to open source and Gerrit code reviews since our inception. I feel like in the last year, we've probably been contributing to a fair bit to JGit as well, which you'll see in this talk. We help companies with the Gerrit installations and contribute back to the open source community as much as we can. What we're talking about today, Gerrit and JGit and how they get the most out of each other. I think some of our friends here use CGit for their Git maintenance stuff like the GC and all. We at GerritForge, we discourage that because there's some optimizations that JGit does that Gerrit can then make use of. And if you use CGit to make the GC, it can't make use of those certain optimizations, right? So that's why we call it a love story like no other. I'm Dani. I'm an engineering manager at GerritForge. Help a bunch of customers scale their installations. I'm also a Gerrit contributor and a community manager. So what we'll talk about today, we'll do a brief overview of Git internals. I always find those quite interesting and confusing as well. So hopefully today we answer a few questions. We'll talk about phases of an upload pack, which these also end up being reused in a bunch of other scenarios. And finally, we'll talk about improvements to JGit and Gerrit to reach warp speed. But first of all is why would we need warp speed, right? Like Gerrit is not that bad. Why do we really need to push it so much? And the answer to that is GHS, which I don't know if you guys know what it is, but it's our AI-driven tool to maintain SCM health and stability. We talked about this at the Munich meetup 3 months ago now. There's the recording on our channel on YouTube if you guys want to look at it. Quite an interesting project. I'm sure we'll talk about it at future events as well. But anyway, why would this need warp speed? Essentially, being a reinforcement learning algorithm, it needs to learn and train on real life data. So we wanted to reproduce years of work in just hours. So we really needed to push the performance of what we could do with Git. So let's start with looking at what goes on in a Git server to begin with. Repositories are structured via objects, so objects are the core of the repository, and they combine in very interesting way, as we'll see in a second, to create a larger graph or representation of the repository. There's 4 types of objects. We have tags, commits, trees, and blobs. And finally, we identify them by their object hash of their content. So it looks a bit like this. So we have tags. You can reference tags. Tags reference commits. Commits can have commits have trees. Trees can reference other trees or reference blobs. And blobs, so you can imagine trees as your directory structure on your file system, and then blobs are your files, essentially. All right. And I forgot to say commits obviously reference trees, but can also have parents. So a parent of a commit would be another commit, or it could also have 2 parents if it's the result of a merge commit. All right. So because of addressing everything but the SHA-1 of their content, Git is referred to as a content addressable data store. So if you know the content of what you're looking for, you can find it. That sounds a bit stupid because it's not really useful if you need to know what you're looking for to search for it. So that's why we have branch names. So for example, when you say main, that's essentially a friendly name for some content, all right, that you can address in a friendly manner. So how are all of these objects stored on disk? So there's 2 main formats, loose objects being the simplest in a sense, each file represents an object. So literally each file that you push, each tree, each commit, it will be its own file on disk. And the file name is going to be the hash of that content. That has interesting repercussions later on. But yeah, you don't address them by the file name. It's actually the hash. You can see how this becomes quite quickly unattainable, as in if your repository becomes massive, you don't want to have, well, not even massive, even just a normal size repository. You don't want every single object to be its own file, right? But anyway, on disk, we represent them like this. So if you guys have ever looked inside the .git/objects folder, this is obviously a very simple repository, but you're going to have a bunch of those 2-digit folders. Those are going to be the first 2 digits of the SHA-1 of the content. And then if you go into any of them, you're going to have a list of files. So this is a file. And the name is the remaining bit of its SHA-1, right? So the full SHA-1 of that will be 0193 blah, blah, blah. So if you can look at this by doing a git file minus t of the SHA-1, it will give you then the type of the object. And if you do minus p, it will actually give you the content. So here you can see how you're addressing. So you can see there's blobs that have got that SHA-1, and that's the file name related to it, right? So if you did a git file minus t of that SHA-1, it will tell you that it's a blob. And if you did a minus p, it will actually show you the content of that file, okay? The other optimized way of storing objects is pack files. It might sound a bit counterintuitive, but really in Git it's more efficient to have one massive file with all the objects bumped into it. And these objects are stored in a continuous manner, right? So you have literally, it's just a list of objects, and if it wasn't for the index file associated with each pack file, they wouldn't know who's who, okay? We'll look at the details of this later on, but essentially pack files are a store of multiple objects with an index file associated to it that tells you where each object begins and ends. Now, so yeah, here you can see you've got your 2 pack files, your 2 index files, and there's a file I haven't mentioned so far, and it's called the bitmap, which we'll talk about a lot in a second. And here's the crucial difference between using CGit and JGit. They create this bitmap in different ways, and they are invalidated in different ways. And so the JGit bitmap is much more optimized for how Gerrit uses it, while the CGit one, it has nothing to do with Gerrit. So yeah, it's not quite as optimized, and you don't really get as many benefits. So yeah, we'll talk about that more in a second. Now, zooming out a second, I'm a user, I'm just doing a git push on the server side. In the JGit world, this is called the receive pack. It might be a bit counterintuitive, but as a user, it's counterintuitive, but as a server, it makes sense because I'm receiving data from the user. So when the user does a git push, it creates pack files on the server. So your commit stuff is stored as a single pack file for that commit. It's separate from other commits, but your commit is stored as its own pack file on the server side. While when you do Gerrit UI interactions, that creates loose objects. So this is different between GitHub and Gerrit or GitHub, because GitLab and GitHub use a database. They don't use NodeDB. So they don't even create anything on the Git repo. They just create an entrance in the database, right? But Gerrit using NodeDB, it creates loose objects, which then need to be garbage collected together with the pack files that we just created, right? So what about serving Git data, which is what we were going to talk about today. So this is called an upload pack. Again, maybe counterintuitively from the client side, but from the server side, I'm uploading data to the client. So that's why it's called an upload pack. So yeah, 2 main things, a git fetch and a clone. I assume we know that if you do a git pull, really you're just doing a fetch and then a checkout or a merge. Anyway, so yeah. What happens in this case? So there's 6 phases that Git identifies when serving an upload pack: negotiation, counting, search for reuse, search for sizes, compression, and writing. So now we'll talk about in detail about all of these. Negotiation one is quite interesting for me, at least. So let's pretend that this is our simple repository, okay? So I've been on holiday, as Ponch knows, for the last week or so. So the latest state I've got since before I left is on the bottom here, and it's my client side. I've got my have, so I've got commit A, okay? But these guys have been working, luckily, and so the repository has moved forward, and now the latest state is commit D. So what happens when I come in the office, I sit down and I do a git fetch. So I'm requesting the latest version of that branch. So tell me what's happened since I've moved over. And the server sends the latest SHA-1. Commit D obviously is not a SHA-1, but for sake of simplicity, the server will say, look, this is the latest one. So, the client will then respond saying, I have commit A and I want that commit D, all right? So now the server needs to start thinking, how do I represent the graph? How do I reconstruct the graph so that the client can recreate it starting from the point that I know he has, okay? So this is called the counting phase now. So yeah, we want the whole graph, and we still have our commit A. The way Git works is it first traverses all the commits on a higher level than the simple object. So it starts from commit D, it then goes to commit C, goes to commit B, and then goes, he's got commit A, I can stop traversing commits. And then it needs to traverse the remainder of the graph. It needs to find all the other objects that it needs to send to the user. So 3D, C, B, and then all the blobs, right? So it's not hard to see how when the repository reaches any decent size, this is going to take some time. And it takes time, and then you need to scroll through all the loose objects, through all the different pack files, figure out where everything is. It's an intensive operation. Clones are really not our friends either, because a clone doesn't have anything. So everything becomes the want. So a client just say, right, I want everything, right? So at this point, we redo the same thing, and we need to traverse the whole graph every single time, right? So just wanted to guys make you feel the pain. I need to traverse the whole thing, right? So this is pretty intense. And obviously it only gets worse over time. As the repository history grows, it's not going to get any smaller anytime, right? So it only gets worse. Introducing bitmaps. This is nothing we've done. This was introduced by Google in 2013, so it's nothing new, but I always feel like it's something quite obscure, so always good to re-go over it. So essentially, bitmaps help us ask what objects can I reach from this commit. So it's a reachability index of each object. So each object in the repo has a bitmap. Okay, so when I say that there's a bitmap file, it actually contains a bunch of bitmaps inside. It helps us understand, as I said, which objects are reachable from a given commit. So although there's a bitmap for each object, we tend to use the commit ones. So that it tells us, you'll see in a second, but it tells us which objects I can reach from that commit. And each bitmap file contains multiple ones. So it's generated at GC time. So this is important. So when you run git GC, as well as packing everything in a single pack file, Git, or either JGit, CGit, doesn't really matter, it generates the bitmap. So once it's compressed, it created a single pack file, it then generates the bitmap. Now, interestingly, CGit has actually added the ability of having multi-pack bitmap indexes. So you can have bitmaps that span multiple pack files. And then that can be used in interesting ways with geometric repacking and all of that. JGit doesn't support that, so we can only have a bitmap for that individual pack file. It looks a bit like this. I'm going to re-go over this again because I know it's a lot of information on one slide. But essentially, commit C, being a bit newer, can reach every object that is older than himself. Commit A is a bit older, so it cannot reach anything that's newer. Okay, and then if you do and not, so C and not A, it tells you what objects you need to reconstruct C. So optimizing for scale. This approach requires two bitmaps, as I just showed. The bitmap for the want, so the server will go, okay, he wants commit A, let's find it. Does it have a bitmap? Yes, fine. Don't need to traverse anything else. Now, it wants D, starts and looks for D, so it has no bitmap, it needs to traverse, so we go to commit C, finds a bitmap, great, it stops there. It doesn't need to traverse anything else in the whole history, right? Now, in this example, this might sound like you don't save much, but when you've got like, I don't know, the Linux kernel that's been going for 20 years or anything substantial really, everything is going to be in your bitmap really. And only the newer, like the most recent stuff is not going to, everything that's been introduced in the repository since the last GC won't be in the bitmap. So maybe it's the last day, or maybe it's the last 2 days worth of work, but it's not the last 20 years that you need to traverse, right? So this gives us a massive performance boost. We still need to traverse the objects that are not in the bitmap, but you don't need to traverse everything else, okay? So now we can compute the set difference between A and C, as I was showing earlier, maybe a little bit clearer, hopefully. But this is able to tell us really quickly that I need to find commit B, C, the trees and the blobs, and send them over, okay? So this is the counting phase. Now, compression. Now, we haven't done a mistake here. We're gonna skip search for reuse and search for sizes for now, because I want to explain how the compression phase works first, and then hopefully the other two phases make a bit more sense afterwards, okay? This is the time that JGit has spent compressing objects, pretty obvious. It doesn't actually track CPU time. It rather tracks like the lapsed time. So this can be done in parallel. We'll show now what full object versus offset delta means, but essentially we have some full objects, we have some delta objects. We can combine those in interesting ways to optimize what we're transferring over. And finally, we call this a deflated compression, which is a lossless type of compression. Obviously, we don't want to lose any information regarding the history of our data, right? So it looks a bit like this. Let's say that we're looking at this specific Git diff. So this is for a file called Git version gen, whatever, doesn't really matter. And we've only changed one line in this file, right? So obviously it would be pretty wasteful to just restore the whole file just for the sake of it, right? And then imagine doing that for every single change that you do to your repo. Doesn't scale. So what Git is able to do, and this again is what happens also at GC time. It's able to compress everything in this format here. So you've got your base object. So this is representing the tree related to this commit. It's not representing the file itself. Just picked an example because it was a bit easier to explain. But it's able to say, look, the other files haven't changed, so copy that bit over as it is. This SHA-1 of Git version gen has changed, because now you need to refer to a newer SHA-1. So change that bit, write that bit that we will highlight it in green, and then the remaining of the file, it's still the same. We just do the same. So this delta compression information is actually stored in the pack file, right? And then when you go to inflate it, it will show the decompressed object. That's how you can reconstruct it. So in an index file, it looks a bit like this. You've got, I don't know if how many of you guys know the git verify pack command. I find it quite interesting sometimes. But what we're looking at here is the index file. So not the pack itself, but the index file, okay? So let's look at a whole object. So this is a full object and a delta object, okay? So this is the difference I just spoke about. So the full object, here you've got the SHA-1, the type, so this is a commit, the original size, the size in the pack file. So you can see this has been compressed a bit, and the offset. So you can find this commit, this object, offset 13,477 in the associated pack file, okay? And this is how we can find these objects, and that's valid for everything else. However, if we look now at a delta object, so this is a tree, so the example I just spoke about, and it tells you that there's a depth of 1, so it only needs 1 hop, let's say, to be reconstructed from this base commit, okay? So if you apply that object, if you apply 8CF6 blah 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 to 02EA, you're able to reconstruct the full object, okay? Now this can come at the end of the verify pack. It will give us this that I found interesting, this summary. So in this file we've got 310,000 objects. There's 23,000, what is it? Is it 23? Yeah, or 2,300, can't see from here. Objects that have got a 1 hop length. So you need, there's a certain amount of objects that you need to hop at least once to reconstruct fully. And there's 5,000 objects that you need to hop 8 times to reconstruct fully. So that's like, I've been optimized over time. You can see next to tree, you can see the difference in size between 02EA and 8CF. So the first tree was 204 bytes. And now the deltified object is only 6 bytes. So that's a massive, massive compression there. Thanks, Ponch. Now, back to the search for reuse, which is a phase that we've optimized a lot. This is actually a quite complex phase, and I think it takes 90% of the execution time of a fetch. So optimizing this is where you're going to find the biggest wins. So it's the time that JGit searches for deltas that can be reused in the way that I just explained for the compression phase. So we scan all the pack files, searching for the best representation of the object that is being requested. So in our example, say that we have ABC is the object that the client has, and it wants XYZ, and the best representation happens to be ABC plus DEF, okay? We look in the first pack file and we find ABC, great. We look in the second pack file and we find the DEF, great. And then finally we look in the third pack file and we find XYZ. Now, the server could just send XYZ, but that's going to be a bigger, more inflated representation of that same object that he knows he can build by just doing ABC plus DEF. He knows that the client has ABC, so it figures out that it only needs to send the DEF, the delta, to the client for it to be able to reconstruct the object. So yeah, this is pretty cool. Finally, the search for sizes. Now, because of how Git works, it's actually able to understand this compression and what it can use to rebuild both objects a lot easier, because if it knows the sizes beforehand, because all it does is it compares objects based on sizes. So if we tell it the size beforehand, it's able to do this optimization much quicker. The writing phase. So now it creates a pack file with only the single object that we need to send, not the whole repository, not everything else, not X, Y, Z, just the EF, because it knows that the client can recreate what it needs from the object, creates it in memory, and sends it over to the client.
Hello again. So I'm Ponch. You probably saw me around previous GerritMeets or Gerrit User Summits, or been with GerritForge for I probably started in 2017 or around there, so I can't even remember. I've been a contributor since then. So Dani so far has been showing you the colorful part of the presentation. I'm gonna go through like a shopping list, basically, of changes that we made to improve both the write part and the read part of Gerrit itself. And just to reiterate why we ended up in this situation, why we ended up doing this deep down in this code, is that because we were working on GHS, so we wanted to optimize the right side of Gerrit, because we wanted to train our AI model. So we wanted to basically reproduce, simulate years of traffic in a short amount of time. On the other hand, on the read side, we wanted fast feedback. What does it mean? It means that we wanted to see how fast clones were, how can we push the clones to be faster, how can our GHS tool can actually impact our repository, and the GCs as well. We also wanted to see how we could improve the GC operation. So I divided the changes into chapters, let's say JGit improvement and Gerrit improvement, and for each of them there is like a sub-chapter, which is the operation we're going to tag for that particular change. And I'm gonna give a prize to each section, which is basically my favorite change, which usually is the smallest change, which gives the higher benefit to the code in terms of performance. Now, let's start with the upload flag for Git. The first change we introduced is this, as you can read, we basically introduced a configuration which is called quick match search for use config. So what this change does, as Dani was explained before, when he was explaining the search for use phase, Dani was saying, wow, we need to go through all the pack files to find the best representation on the object that we are after. Okay, fair enough. So in Dani's example, we had 3 pack files, but imagine your mono repo start to have like 10 million pack files. Well, you're gonna do it over and over and over. It can be quite expensive. Now, what we did with this configuration is basically allowing us to decide if we prefer time over dimension. What does it mean? It means that when we are after our object, we can even decide to have the best representation of it, which translates in transferring the least amount of data to the client, or we don't care, we just want to be quick. So that's what we did with our change. So we introduced this configuration where you can say, look, I don't care about the best representation, I just want to be fast. So just bail out as soon as you find a representation of the object. And that's something that it really speeds up things. And also what it does, it looks for the most recent pack files. So it traverses the most recent pack files and it prioritizes the one with the bitmap, because again, tying back to what Dani was saying is that if you have a bitmap, you go fast, you get a really high boost. So that's it. Those are our candidates that we're gonna look for, for our objects into. So that's the first change. Coming up, second change. Again, here what we are doing is just preloading some data into memory. Why? Again, quite expensive, as Dani said. We need to go loop through over and over all the pack file. Well, so what we did, we just store some information in memory. So we just added a map, an hash map, with the SHA-1 of the object and the actual representation of the object. So we avoid to go and scan and read on file, bring it in memory, and store it in an object. And that's a huge improvement. Basically, we went from a quadratic to a linear complexity, which means if you have a 1 million object and 10 pack files, we went from 10 million scan to basically 10 scan, which is quite a huge improvement. Optimize search for a suitable map. So this change was basically, it wanted to, first of all, align the logic in CGit and in JGit, because they were misaligned before this change. And what we are doing here, we are trying not to use the first bitmap that we found in a pack list, but rather the latest one, because the latest one is more likely to be the one that comes from a recent GC. That means you have fresher data. It means that most probably we have those objects in our bitmap, so we can really be fast there. So that's what this change does. It basically switched the way the list of pack files and are scanned. Now, next in line, and as you can see, that's my favorite one, with some thermal condition that we're going to talk about in a second. So we switched so as it is today, JGit uses a custom encoding method to encode string to bytes. Now, we find it out, actually Marcin found it out, so kudos to Marcin for this change. And it was like, okay, why are we using a custom one? Let's see what happens if we just plug in the standard Java encoder. And wow, we had a 15-fold improvement in the performance. So we were like, wow, that's quite impressive. And so I did a bit of digging in the code to try understanding why the hell we're using a custom one. Well, the answer is, I don't know yet. Why? Because so this standard with this custom encoder was there since the really beginning, literally the initial commit that you have in the repository. So we're talking about 2009. Well, so I don't know, and there are no comments around. Unfortunately, there are no commits, explanation, or whatever. So we need to guess a bit what's going on there. Why we have a custom one. By having a look at that, it looks like actually the custom encoder, it does a bit of memory optimization in some cases. So it might well be the case that, in some cases you might want to have a custom encoder, but in my opinion, that should be at least configurable. It should be something that should be considered on case by case, because basically you need to decide if you want to pay your price in memory or in performance. And as you can see here, we're talking about 15-fold. So it's a big price to pay. So as it is, the change is just switch to the custom Java encoder. But in my opinion, maybe we should revisit the change and see if we can make it a bit considerable, and if we can do some benchmarking around that. So as I said, this change is there, but yeah, with some term and condition applied. And so this was the last one for the first chapter. Second chapter we're talking is receive pack. So this is the right side. And Dan has been talking a lot about the read side of Gerrit, not that much about the write side, so not that much about receive pack. And this change, what it does, is basically it allows to customize the pack ref lock intervals. What the hell is that? I don't know if you guys are familiar with the packref file, but it's actually a file that you will find in your .git repository, and is basically a mapping between a reference and the object that the reference is pointing to. Now, this file is updated every time you write on Git, which means every time you do the AGC, but every time you have a receive pack. Okay, so that means that if you have a write intense system, you have a lot of conflicts and lock on that specific file. And in JGit, there are some poses. So there are some poses configured in like an exponential backoff manner, which are of 0, 100 milliseconds, up to 1.6 seconds. Now, and these are coded at the moment. There is nothing that you can do about that. But a receive pack can be way faster than that. In our experiment, we got up to 4,500 receive pack per minute, which turns out to be like 13 milliseconds per operation. And as you can imagine, it was like a high concurrency situation. So every time we were having a conflict on that log file, for an operation of 10 milliseconds, we were waiting at least 100 milliseconds, which is like 10 times more, which is a bit of, unbalanced wait. Furthermore, the interesting thing here is that the sleep that you have in a code while you are waiting for the lock to be free, it basically blocks the incoming thread. Okay, so without releasing it, that means that you can end up blocking the full thread pool. So basically, you're there just waiting for X milliseconds, and you cannot have any incoming write anymore. So that was like a big thing for us. So we introduced this way of customizing it. So it's just a configuration. You can put whatever you want, and that's something that has to be tied to your system, because it's something that depends on the file system speed. So 100 milliseconds, maybe it could be, a good, a reasonable value for like a slow file system, but nowadays probably you have something faster. So that's something that has to be tied to it. Next one in line, we have this one: do not iterate over or refs to find the peer ref. So what are we talking about here? So a peer ref is, let's go back to our packed ref. So whenever you have an annotated tag, as Dani was saying, an annotated tag is actually an object, is one of the 4 fundamental building blocks of Git. An annotated tag is an object itself, so is not directly the object is pointed to. So to understand where an annotated tag pointing to which object is pointing, you need to peel it. So in Git, we say that you need to peel it. Somehow you need to loop through the graph and understand what you're pointing to. And in the packref, the annotated tags are marked in a way where you can straight away see which object you're pointing to. Now, what JGit is doing, here at the very top, you have this header, which tells you what's inside your packref. Here we're saying we have peeled ref, fully peeled ref, and our packref are sorted. Okay, fair enough. But by definition, you always have peeled ref in this file, because like your ref as master is by definition a peeled ref, is pointing already to a peeled ref. So what JGit was doing, it was iterating through all the ref to understand if you had a peeled ref inside it, which is always, it doesn't make sense. So much that if you have a look at the CGit code, CGit doesn't care about that. It just has a statical header that just writes in the packref without doing any operation. That's it, end of the game. So what we did here, we just aligned the JGit code to the CGit and we're basically skipping this unnecessarily linear operation. And again, kudos to Marcin on the first place of the podium. Now, last chapter of the JGit improvement, GC operation. So generation of the bitmap in parallel, that's what these changes does. You might say, but bitmap are already generated in parallel. True, but not true. As in, true in the sense that they are generated in memory in parallel, fair enough, but when you write them, they're not written in parallel. So what we're doing here, we're written them in parallel, and so this change speeds up, in particular, the writing part of the bitmap. I don't know if you guys have in mind, but whenever you do a JGit GC, the GC will print out all the phases which is going through, and one of them is this phase, the writing phase of the bitmap. And here you're going to have a boost that depends on the number of cores that you have on your machine. There you go. Last chapter, Gerrit improvement. We're just going to talk about receive pack. So first one is the delay in the formatting of event whenever you have a change merged. So basically what we are doing here is like, well, if there is nobody listening to my events, why the hell should I bother even formatting them? That's the chain. That's how simple is the chain. We are just skipping the formatting of the event whenever there are no listeners for these events. And formatting an event is quite expensive because you need to create the JSON payload of that format of that event, which means that if in that event you are referencing an object, for example, let's say an account ID, you will have to explode that object. So it's kind of a recursive thing that can go on and on and on. So it's a really CPU and memory intensive operation. And that's what we're doing here. We're just skipping it if it's not needed, pretty much. Similarly, in concept to the previous one, do not format email if you don't need to send them. Why would you bother? Again, and this is the winner, and kudos to Luca for this change. Similarly, the logic is similar to the previous one. So formatting the email, again, is really expensive because you need to explore all the information, you need to parse your SOI template, and so on. But Gerrit internally has a really complex heuristic on when you want to send an email and not. In particular, after the introduction of attention set, we've been really focused on try to not be too spammy. Let's say, try to really communicate with the user whenever you need to. So the heuristic done by Gerrit behind the scene is quite complex, and that's it. So what we're doing here, again, we're just skipping the formatting email if it's not needed, and that's it. And you really see the benefit. We had some customer that they were having, they have like small instances. Gerrit was a bit under pressure, and we could see the mail queue going up, and we were like, for sure it's the mail demo that cannot cope with the delivering the mail. But then we realized that no, it was Gerrit that because it was under high load, it couldn't handle this formatting of the mail. So that's another nice change that we proposed. Last thing I wanted to tell you guys before the question, not all these changes has been merged as yet in JGit or Gerrit. So I put the link on all the slides with the change. So if you have any further consideration to do, you can just go there and add your comment to the change, and it will be appreciated. And that's it.
So Muzab from Arista Networks is asking, what is the negative impact of a large number of change set refs in ref changes stars? Like if you have 1 million refs for a particular repo.
So actually, that makes a big difference if you use, I would say, JGit or SIGIT for doing GC. Let me explain you why. So if you have a lot of changes under ref changes, sorry, a lot of refs under ref changes, and then a lot of objects under ref changes. If you just do GC using SIGIT, so SIGIT will be completely unaware of the fact that those are changes, those are no heads, those are no tags. For SIGIT, they are just refs. That's it. So when you do all the operations that SIGIT typically does, so GC, repacking, and everything will be unaware of that. Also, with regards to the formatting of those refs into the file system, so if you use JGit, of course, you can benefit from ref table. On SIGIT, you cannot unless you use the latest and greatest of SIGIT that actually has support for ref table. But at the end of the day, you need to be a bit careful because the support in SIGIT just started. In JGit has been there for a very long time. So if you are in that situation with millions of ref of changes and you are using, let's say, SIGIT for the maintenance of your repo, think again. We did some specific experiment of helping one customer that was saying that the GC was not effective enough and they were using SIGIT for doing GC. We moved from a bitmap created with SIGIT to a bitmap created with JGit. So in terms of generation, the bitmap was 10 times faster, right? And in terms of effectiveness of the bitmap and the pack files organization was the same repo with the same GC done with SIGIT or with JGit. With JGit was able to improve the performance of the clone by a factor of 2, so twice as fast. So if you are in that situation and you're using SIGIT, think again. Try to use JGit as much as possible.
So then next one, what is the rapid pack index? Sorry, the rapid pack index really looks like the multi-pack index. Why not just implementing the multi-pack index and bitmap in JGit instead?
Yeah, I believe actually it's a good question. So it's a good idea. I believe NASA was asking the same thing later on. When are we going to implement the multi-pack index in Gerrit and JGit specifically? Yeah, I'm all for it. So if anyone volunteer to join the endeavor, yeah, let's work together. Let's get it done. I believe it should be absolutely done. With regards to, there is one small difference though. So if you do the multi-pack index, is a one-off and then is obsolete again, right? So because the packs they are created after the generation, the multi-pack index, they are not in the multi-pack index. Of course, you save some time because the ones they are in the multi-pack index, they are using it, but the others are not. Also, second thing, if you want to have, for example, if you use geometric repacking, if you want to have a good organization of your multi-pack index, what you should do is basically do it continuously. And even if multi-pack index, the generation is quite quick, then if you do continuously, then you're eating up a lot of CPU. Whilst on the other side, if the fast index lookup is extremely cheap to calculate, and is always up to date from that point of view. It doesn't impact the disk. Last but not least, when we will implement multi-pack index, I really want to get it done on JGit, we'll need to be careful on still keeping a kind of preference on the view that Gerrit requires on the pack files. As you have noticed, for instance, when you do, for instance, a GC on a SIGIT, your aim is to create a single pack file that contains everything, but actually JGit does something different, isolates the changes from everything else in different pack files, because that gives a lot of boost in the isolation. When we will implement a multi-pack index, we will need to make sure to preserve that kind of preference for Gerrit as well, in a way that we don't lose that advantage.
I saw an interesting one. Most of these changes are work in progress and marked as do not merge. Why?
So I actually had the idea to flag it as do not merge for one main reason. So we were focusing on basically going as fast as possible, but not necessarily to do in a super safe way. So basically, as soon as we start, let's say, productionizing them, in making sure that they are absolutely safe, then we will remove the do not merge and say, okay, now it's time to go and do things a little bit more cautiously in order to make sure that we are not breaking anything from here or there. But in our rush, we want really to see how much we can make JGit faster, right? And in that rush, we really wanted to go and hit every single bottleneck one after the other. And that's why we want to, let's say, to save time in review by saying they're not ready. It's like a work in progress. They're not ready really to be reviewed, and they may not be merged because maybe we think again, we think that they are not safe. But the one that Ponch presented, I believe they are absolutely safe. I remember that I suggested to Ponch to remove the ones that are a bit controversial and may be too aggressive in terms of performance improvement.